Aloha geologists. I know that's a new scientific term. It seemed like we were only biologists for a very short amount of time, and hopefully we will get a chance to go back and explore biology later in this year. Biology being the study of plants and animals and living things. Biological material. But now we are geologists for this unit, and geologists study the Earth. We study what makes the Earth tick, or how it is shaped. We're going to be studying some rocks, and some soil, and some minerals, and how all of those play into the big picture of our planet Earth, and how it was formed, and how it is constantly changing, even under our very feet. So this is Unit 4 of CKSCI, processes that shape Earth. As you can see, we've got a lot of interesting rock formations that we will be learning about. And this is not the only time this school year that we become geologists. A lot of the information we're learning now in these videos that we're going to try to get done before we go on our winter break, we'll see again in the third or fourth quarter when we get to Unit 6 of CKLA. So, learning about the world around us, the Earth under our feet, how we have the mountains, and how we have the valleys, and how it all came to be. So, as a quick overview of what we can expect in the next week and a half that Mr. Chambers will be making these videos for us, we've got Earth's shifting pieces, how pieces of Earth are constantly moving. We've got more evidence of Earth's shifting process, so more ways in which the Earth changes. We'll be learning about earthquakes, tsunamis, volcanoes, erosion, and landslides, and how all of those change the world around us, and how they are affected by the moving tectonic plates of our Earth. So, I know this is a very quick crash course into geology. And I know that we are also focused on getting that time in an exact path in our afternoons, and trying to finish up our reading of Sylvia and Aki, and doing something with CKLA. Still haven't quite decided what that will be once we're finished with our test, but we have about 2 weeks before we go on winter break, and a lot of information to go through. So, to start off here in Unit 4 of CKSCI, we're starting on Chapter 1, Earth's Shifting Pieces. And right away, anytime I'm reading an informational text such as CKSCI, and I see that I've got big questions or vocabulary, that's where my eyes should gravitate towards, because that tells me what I'm looking for in this chapter, and helps me be familiar with some of those new to me words, or words that I've heard but wasn't quite sure what they meant. So our big question for Chapter 1 is, why are some fossils of the same type found thousands of miles apart on different continents? So we're going to learn that fossils appear in different continents. Those continents could be Europe, Africa, Asia, North America, South America, Australia, or Antarctica. And how did those fossils, those remains of plants or animals, wind up on different continents so far apart? Well, first and foremost, to get started, we know that we're looking at fossils and how they separated. But what exactly is a fossil? Well, a fossil is the remains of an organism preserved in rock form. Any living thing, insect, plant, animal, human, as long as it's been preserved and hardened, then it is a fossil. This can be the bones and remains of a living creature. It can be the imprint of a big plant that we had. It is any living thing that has hardened into stone, or stone has hardened around it. And our second vocabulary word, how I introduced you today, you are a geologist for this unit, and a geologist is a scientist who studies what Earth is made of and how it changes over time. So that's what we're going to be doing in the very short week and a half that we'll be going through these 7 chapters. All right. Starting off. The eastern coast of South America contains the fossils of a reptile that lived hundreds of millions of years ago. Fossils of the same reptile can be found about 5,000 miles away in Africa. South America, Africa, 5,000 miles away, yet we still have fossils of this lizard. How did that lizard cross the Atlantic Ocean? Where's that coming from? Geologists are scientists who study the Earth, including rocks and the fossils of extinct organisms. Geologists found an interesting pattern when they looked at particular kinds of fossils. These fossils are discovered far apart across oceans. These animals couldn't have traveled those thousands of miles that now separate their fossils. This presented geologists with a problem. And as good scientists, those geologists came up with a question. And so that question is, why are some fossils of the same kind of organism found thousands of miles apart on different continents? Well, that's the big question we as geologists want to answer. So we're going to look at the research of other geologists to see what they have found out. So here we have a picture of Africa and South America and the fossils of Mesosaurus. Mesosaurus was a reptile that lived long ago. Its fossils have been found in both South America and Africa. And this is one of the earliest clues that make scientists go, how did it get here and here so far apart? Well, that's all due to Continental Drift. Albert Wegener, who we will read about more in Unit 6 of CKLA, provided a possible answer to the fossil evidence. He was a scientist who noticed how some of the continents appeared to fit together. Could the continents once have been close together and slowly moved apart? Wegener gathered evidence that supported this idea, which he called Continental Drift. One type of evidence used to support his theory was the fossil record. After studying fossil evidence, Wegener concluded that these continents had once been clustered together. Wegener's theory was incomplete. It's just an idea. But it was the beginning of the study of Earth's plate and how they changed over time. So he has 2 parts. He's like, hey, you see how Africa and South America look like they could fit together like puzzle pieces? And you know how I've got some of the same fossils on Africa and South America? What if at one point they were all one? The only thing he didn't know is how they split apart. It makes sense that they might have been together. The continents' shapes look like they fit together. Their fossils look like they could belong together. But how are they moving? Well, we'll find out. So here we have an example of fossils found across different continents. South America, Africa, the subcontinent of India. It was its own place until it collided into Asia, creating the Himalayas, where we have Mount Everest and K2 and several of the other tallest mountains in the world, all because they collided. Australia and Antarctica. We have fossil remains of the Cynogenathus, an extinct land reptile approximately 3 meters long. We have here in India fossil evidence of the extinct land reptile Lystrosaurus. South America, Africa, and maybe Antarctica, we have fossil remains of the freshwater reptile Mesosaurus. And across South America, Africa, India, Antarctica, and Australia, we have fossils of the same plant, a fern called Glossopteris, which was found in all of the southern continents. All of these have fossils of the same thing. Some living organisms over here, some living organisms over here. It shouldn't be that we should find fossils of the exact same thing in all of these locations. Well, how this happens is with Earth's crust. Not that outside of the pizza that you should eat. You probably don't, knowing that you're fourth grade, you probably throw the crust of your pizza away, but the crust is the best part if you're eating quality pizza. I digress. We have a new vocabulary term, a plate. Not what your pizza is served to you on, but it is in geology a large fragment of Earth's crust and upper mantle. It gave us more vocabulary terms that we have to understand before we fully comprehend, but a plate is a large fragment of crust. But what is Earth's crust? Well, scientists now know that Earth's crust has different pieces called plates. These plates move and interact over large spans of space and time. Sometimes it is obvious when plate movements occur, such as if a group of islands pops up out of the sea after an earthquake. Most of the time, though, the movement of plates happens too slowly to notice. Here's a map of the Earth broken up into plates. And these plates are huge, thousands of square miles, and deep, about 5-6 miles deep, of either continental or oceanic crust, where we have places like Australia and its whole plate that it is served on. Here we have the North American plate and the Caribbean plate. And some might be familiar with our neighbors over here, California. Well, they're also part of the Juan de Fuca plate, and that keeps moving on us, which creates a lot of earthquakes. And this is only just a sample of what the plates that we live on kind of look like. It's hard to see what these are. You can't go out and be like, here's a plate, here's a plate, here's a plate, just like you can't go out and be like, here's all of the city, here's all of our state. There are boundaries that are unseen to us. As geologists, they can piece together and be like, okay, based off of certain things, we can tell that this might be the plate boundary, okay? But can geologists observe and measure plate movement? We can. One tool that we can use is the GPS, or Global Positioning System. The same thing that's in your phone that tells you to turn right or turn left when you ask for directions. Well, GPS receivers are placed on different plates. They communicate with satellites that orbit Earth. The system locates each receiver and measures the distance between them. Scientists use these data to measure changes in the distances between receivers. So through GPS, they can say, hey, we put these 2 points here. They're moving apart, they're moving together. But it takes a very long time for that data to come in. So we kind of have a rough idea of what plates are. Giant slabs of crust that are moving. But how or why are these plates moving? Well, liquid rock below Earth's surface is known as magma. It is very hot, and the layer of Earth where magma forms is called the mantle. Beneath the mantle lies Earth's core. The core has 2 layers, the outer core and the inner core. The outer core is more molten than the inner core. Both layers of the core are made mostly of iron and nickel, 2 very common metals. The core is very hot at 10,800 degrees Fahrenheit, or about as hot as the surface of the sun. The intense heat from the Earth's core plus pressure from above produces currents in the mantle. These currents help transport the plates across Earth's surface. This helps to explain how land masses and fossils that once were located close together can now be found thousands of miles apart. The movement of plates is one process that shapes Earth. All right, before I get into this diagram here, there is a word for us to know. It is molten. Molten means it's liquefied. It is usually used to describe liquefied substances that are normally solid, such as metals and glass. So it is hot enough that all the metal, the nickel and the iron, is melted. It's molten. It's liquefied. Okay? But all this happens down in our inner core, where all that metal is melting or being liquefied. And it slowly rotates around the outer core. And as the inner core rotates, it also moves the mantle, which we have a lower and upper mantle. And it's all very slow moving magma underneath. And that slow moving magma also moves the crust, this outer layer, which can be either our oceans or our continents. It moves those slowly, very slowly, like an inch a year, if that, but it's slowly moving, shifting on us. And over millions of years, if all of our continents were once jammed together in a mega supercontinent named Pangea, which we might talk about either later in this reading or in CKLA, how that Pangea would break up into the 7 continents that we know today, and how in the future, as they keep moving in different ways, those plates could collide with other plates and form different continents, where our Earth would not be recognizable to us in millions of years than it was today. Maps would be changing. But that's a lot of information for today. A lot to digest, a lot to ponder upon. And this is only our first chapter. We do have 6 more chapters that we're going to go through real quick in this crash course on geology over the next few weeks. So buckle up and let's enjoy this wonderful ride of science. Thank you for your time. Stay awesome, and I will talk to you real soon.